Alright guys, let's get through 11.2. We've got a lot to cover, but not many slides to do it in, so it's going to be a lot of compact information. Before this is over, you should be able to use Aries Principle. You should be able to find the volume of any shape as long as you understand what the capital B is, and we're going to cover that. And we should be able to find the volume of the cylinder produced, or we should be able to find the volume of a cylinder, and we have to be able to start memorizing area formulas because we're going to learn a shortcut to find volume formulas here really quick. So I'm just going to read over this for you. You're welcome to fast forward a little bit or just pause it, read it yourself, and then skip ahead. But Aries Principle states that if two three-dimensional figures have the same height and the same cross-sectional area at every level, then they have the same volume. What it's saying is if I have two objects that have the same cross-sectional area, and we'll talk about what that means, at every instance from base to base, and they're the same height, then it doesn't matter if they're oblique like we have on the right here. As you can see, it kind of goes, it's not straight up against the square here, and I know that shape's a triangle. That tool is called a square. So on the right we have a right cylinder, right? These lids are perpendicular to the base and they go right along this straight edge. Here we can see, whoa, that I cannot draw a straight line. What we can see here, however, is that we have a straight edge and then these do not meet at the straight edge. So this is in fact an oblique cylinder. This is the same piece of blue tape. This is the same number of petri dishes. I did not move this blue tape, so we can say that from here to here, this line segment is congruent to this line segment. And that's important because Aries Principle says if two three-dimensional figures have the same height, and that's what we're showing here, so they have the same height and the same cross-sectional area at every level, then they have the same volume. Well, I chose these petri dishes for a reason. Each one of these is exactly the same size, right? I mean, they are the same dish, 1 to 1, right? So the top one here is the top one there, and so on. So that means they're going to have the same diameter. Well, no matter where I take my cross-section, let's go red. If I were to take it at this mark on the square and then come here, so I'm 1, 2, 3, 4 up. If I go 1, 2, 3, 4 up, and I go here straight across, that cross section will have the same diameter of the circle. The circle will have the same diameter, which means it'll have the same area. From the bottom to the top of these two cylinders that I've created from petri dishes, they have the same cross-sectional area and the same height. Therefore, we can say they have the exact same volume. And I think that's pretty easy to imagine with these dishes because there are, how many do I have here? 1, 2, 3, 4, 5, 6 dishes on top of each other. Obviously, each dish holds the exact same amount of fluid, air, gas. But now that we have an oblique and a right, they are obviously going to hold the same amount. If I were to drill a hole through each of these and fill it up with water, I would be able to dump the water out of this one into this one, and it would fill it up exactly the same way, even though one is a right cylinder and one is an oblique cylinder. All right, now let's look at this one. The volume of a prism, and a prism again has opposite bases that are congruent. So a cylinder is a prism because it has a circle at the top and a circle at the bottom. A rectangular prism has a rectangle at the top, a rectangle at the bottom, and a shoebox is your classic rectangular prism. A cube has a square at the top, a square at the bottom. A cube is a regular prism in the fact that every face is exactly the same size, and they are all, so if they're all the same size, opposite sides are always congruent. So the nice thing about this here is the volume of a prism is the product of the area of the base and the height of the prism. So if I can find the volume of any prism, I can take the area of the base. That's what big B stands for. That's going to be a little confusing at first. I'm going to take the area of the base and multiply it by the height. So let's look at this example. The volume of a cylinder is the product of the area of the base and the height of the cylinder, where the volume is equal to big B, which means the area of the base times the height, where B is the area of the base. So the area of the base of a cylinder is pi r squared, right? The cylinder has a circle at the bottom and a circle at the top, so its base area is pi r squared. So we can say that the volume of a cylinder is just pi r squared times the height. This works for oblique, and this works for right cylinders. And we're going to do these two right here and now. We're going to pick a radius and we're going to pick a height. I'm going to find my calculator before I get any further because I'm just pulling these numbers out of thin air. I'm going to do a radius of 3 and a height of 10. So I'm going to start with the oblique cylinder. I know that the formula for the area of a circle is pi r squared, and then I'm going to multiply that by my height. Actually, before we do that, let me just point out, well, no, let me not do that yet. So my pi r squared is going to give me pi times 3 squared times 10 for this one. So this is just going to become 90 pi, right? 3 times 3 is 9, 9 times 10 is 90. So I have 90 pi for this one. And then if I come over here, my radius, and that's a nice thing about the radius, I tried to draw it due left, right, to show it's a right cylinder, but I can't draw a straight line on this. This is 3 with a height of 10, and I can do the same thing. The area of the base is pi r squared, and the height times the height will give me the volume. So I have pi times 3 squared times 10, which again is just 90 pi. So if I were to take this purplish pink, and let's say it was a drink, right? And I filled it up, this cylinder, with it. And then, excuse me, and then I try and drink out of it. And it's very awkward to drink out of a non-right cylinder, right? That cup's leaning. Maybe it sat in the sun and melted a little bit. I'm having a hard time. So I say, you know what? I'm not going to drink this out of this cup anymore. I can now take this over here. And if I pour it in, it'll fill the cup up to the exact same level. And the reason that works is because no matter where I take a cross section on this, on these two, right? If I go right in the center and I cut it in half, that cross section is going to look like this. And my radius here will be 3. And if I come back over here to my green cup and I go right to the center, that cross section is also going to be a circle with radius 3. So if you think about it, if you draw a circle on a sheet of paper, and then you can keep stacking sheets of paper with the circle, same radius, same position on top of each other, by the time you have 100 sheets, you'll have a pretty thick circle. And then if you were to take scissors and cut out each of those circles and stack them up, you would create a cylinder. Well, if you had those circles stacked up and you pushed them aside a little bit, they're still going to have the same amount of paper inside the circumference of each circle. So stacking them to the same height will still require the same amount of paper. And that's basically what Aries Principle is. But it's nice to know here that we can do the base, big B, right? So to find the, oh, you can't set your pen to white and see it. That's interesting. So the way I came up with this formula for both of these, again, is just volume is equal to big B, where big B is the area of the base, because this is a prism, times the height. These are interchangeable. This is a substitution where we substitute in more variables, but as confusing as it might seem right now, it's a huge lifesaver later on. All right, let's look at this problem, and I'm going to say it now, just like I've said it a million times in person. when we're solving real world problems, we have to make sure we're using the same units across the entire problem. We can't mix miles and kilometers. We can't mix feet and yards. We need to be in one unit. So as we read this question, let's make sure we're paying attention for that. And here's our question. A contractor is building a sandbox for a playground. The dimensions proposed sandbox are 4 feet by 4 feet by 10 inches. And he has 22,000 cubic inches of sand available. So we need to figure out, do we want to work in feet or inches? Well, I know if I'm going to go from inches to feet, I'm going to divide by 12, and I really do not want to use this, as a problem. It's just going to complicate things. And I know I won't end up with weird fractions if I multiply or make my feet into inches. So I'm going to go ahead and work in inches on this problem. So I'm going to multiply my feet by 12. And this is going to give me a sandbox of 48 inches by 48 inches by 10 inches. And I need to know, does that give me 22,000 cubic inches? Right. So we'll make 22,000 cubic inches, fill that sandbox right up to the top for grand opening of this playground. So now that I have everything in order, I'm going to go ahead and multiply these two together to get 480. And then I'm going to do 48 times 480 on a calculator. And that's going to give me 23,040 inches cubed, right? Here's inches times inches times inches. Inches, inches, inches is inches cubed. And just like we learned from the module, three-dimensional shape gets a cubic rating on its unit. So we have 23,040 inches, cubic inches needed, and we only have 22,000 cubic inches of sand. So will he be able to fill it up all the way to the top? Unfortunately, no. For the last time this year, we have a problem with, actually we have 3 problems with Benito. I'm going to do the first one, and then I'm going to leave the other 2 up to you. This doesn't need to be here. I accidentally posted it twice. So Benito has 15 neon tetras in his aquarium. Each neon tetra requires at least 2 gallons of water. What is the maximum number of neon tetras Benito should have in his aquarium? Now, this hint's really important because we're solving for the volume here in inches, right? And we need to know how many inches there are per gallon, since we're not solving in gallons, which is already kind of weird, and we're not going to ever do that anyways. So first I have to derive the formula for the volume of a cylinder, and I haven't been given that yet, so we're actually going to use V is equal to big B times H, where B is the area of the base. So my base here is a circle with a diameter of 8, so my radius equals 4. That's this 8 inches right here that was given to me. I'm drawing it up here just for clarity's sake, and as I say that, I realize my 4 kind of looks like a 9. So let's do that and rewrite this 4 much more clearly. So my big B is going to be pi r squared times the height. So I'm going to go ahead and make those substitutions. Pi is not going to change, but I am going to have 4 squared times 32, which is just 16 times 32. Throwing that in the calculator, I get 512 pi. So we have that many cubic inches, but 512 pi isn't really helping us here because we don't know exactly what that is. So let's multiply 512 by 3.14, and that gives us 1607.68. And from there, I know that's how many cubic inches I have. And since I know there's 231 cubic inches per gallon to solve for gallons, I'm going to take the total number of cubic inches I have and divide it by how many cubic inches there are per gallon. So 1607.68 divided by 231 is 6.95 gallons. So he basically has 7 gallons available, but he has 15 fish, and each fish needs 2 gallons. So the fish need 2 gallons each at 15 fish, so that's 30 gallons. And he's only provided them with 7 gallons. So in true Bonito fashion, this is not okay, right? 7 gallons is not greater than or equal to 30. His fish will not survive. He didn't make it to the Olympics. He's treating himself, and he's treating himself on this first try to a bunch of dead fish. So he goes back to the store, and in this problem, he buys a slightly larger tank, and he does it again. Checks, well, we're going to do it for him. Will his fish survive? Well, you tell me, and then you can watch the video if you want. And then here, I need you to find a height and a radius that will allow his fish to survive. Send me your answer in Edsby for a little bit of extra credit. All right, that is 11.2 all done. And all you guys need for 11.3 and 11.4 are these 4 formulas. So the volume of your pyramid, that's a square base where everything comes to a point from the vertices of the square. It's 1/3 base times height. Your big B here for a square is just the side lengths multiplied together, right? Length times width. And then your volume of a cone, that is 1/3. Anything that comes to a point, like I said earlier or in the previous video, anything that comes to a point will always be 1/3 times big B times h. Where for the volume of a cone, your base is a circle, so you have pi r squared times the height. And again, since it's coming to a point, you have 1/3. So your pyramid and cone are always 1/3 times big B times h. And then we have spheres. We will cover that right after this in the video. And that is it, guys. We are done with topic 11. I'll have your homework on Pearson. If you have any questions, I'll see you in the Zoom meetings. Northern Hemisphere, or the top half of the globe, and we have South America, Australia, Antarctica, large parts of Africa, Asia, and the Southern Hemisphere as well, or in the Southern Hemisphere. That is the other half of the Earth. We drew it straight to there. We also have the prime meridian, which is that north-south running line that also divides the Earth in half, creating another great circle. And there is an infinite number of great circles that we can find by cutting any sphere, because as long as it passes through the center, you'll create 2 hemispheres. So when I ask what is a cross-section of a sphere, we're not looking at the base. We're considering the hemisphere, or that great circle that cuts right through the middle. So everything above the great circle would be the top hemisphere, and everything below the great circle is the bottom hemisphere. Or if you're looking at it, Florida would be about here on a globe. We're in the northern hemisphere, and we have Antarctica here in the southern hemisphere. It's in the bottom half of the globe. Now, there's something funny here that is actually kind of intuitive if you think about it, but a lot of people don't put that together. The volume of a sphere is 4/3 the product of pi and the cube of the radius of the sphere. That's for the entire circle. Let me move this over to smooth draw. And then we know a hemisphere is half of a circle, right? All right, so we've got that. And let's go back to the PowerPoint. Our hemisphere, it's telling us it's 2/3. Whoops. So let's leave that one there. Oh, did I just erase my other one? No. Okay. So for a sphere, we're going to use this formula. And for a hemisphere, we're going to use this formula. But is it very obvious to everyone watching this video now that 2/3 is 1/2 of 4/3? Well, if it's not, let's do it over here really quick. So we have this sphere here, and I'd say let's find the volume. Well, we know we have 4/3 pi r cubed. And I said, well, I only actually want half of this, right? And that would be, let's say I just say, okay, now what's the volume of the northern hemisphere? If we were to find the volume of this was to be 2 units cubed, then we can divide it by 2 and say each hemisphere is 1 unit. And the entire, both hemispheres together, or the entire sphere would then be 2. But let's see, what is 4/3 divided by 2? Well, I'm going to do it this way the first time. 4/3 times 1/2. That's going to give me 4/6, which simplifies to 2/3. But I know a lot of times, especially before Algebra 2, a lot of people have trouble seeing this right away. So let's do it. What is 4/3 divided by 2? Using the keep, change, flip method. So we're going to keep the 4/3. This is our change to multiply. And then we're going to flip 2 to be 1/2. 4 times 1 is 4. 3 times 2 is 6. And then again, that simplifies to 2/3. So this is why the only difference between the volume of a sphere and the volume of a hemisphere is you divide it by 2.